All right, welcome back. We'll prove theorem 1.4.3 and we'll state it first. Assume that S is linearly independent and that V is not an element of span of S, then I claim that S union V is also linearly independent. All right, so to prove this, I'm going to start with a relationship on S plus V. I'm going to assume that V1 through Vn are elements of S and that A1 through An plus 1 are element of R. And then I want to prove that A1, An, and An plus 1 all need to be 0, and so S union V is linearly independent. To prove this, I'm going to go case by case. First case, what if An plus 1 isn't 0? All right, if An plus 1 is not 0, then I'll be able to do what I've done before, and that's isolate V. So I'll get minus An plus 1V equals A1 V1 plus An Vn. And then V is minus A1 over An plus 1 V1 plus minus An over An plus 1 Vn. So if An plus 1 is not 0, I can divide by it, and then I get a linear combination of V1 through Vn that gives you V, and so this is in the span of S. All right, but we've assumed that V is not an element of span of S, and so this is not possible. All right, so whenever you have a dependence relation like this, An plus 1 is equal to 0. And then if you look back at what you have, I can get rid of that last term, and then what I end up with is a dependence relation in S and since S is nearly independent, the only way to write something like that is to have all the constants to be 0. All right, so first case, not possible. Second case, An plus 1 is 0, and all the other ones are 0, and so that's the only possibility. So we get that all of the constants need to be 0, and so S union V is linearly independent.